Welcome to our presentation of the comparison of supersonic wind tunnel calibration techniques. These methods were performed in the NCSU supersonic wind tunnel.
To calibrate the supersonic wind tunnel, we used two methods. The first method used was the pressure ratio method. The pressure ratio method uses the isentropic relation of the stagnation pressure past the shock wave and the stagnation pressure ahead of the shock wave to determine the free stream Mach number. The second method we used was the Schillerian method. The Schillerian method uses the relationship between the angle of the oblique shock on the object to the free stream Mach number of the flow.
The first method we used to relate the tunnel Mach number to the throat area was through stagnation pressure. The apparatus consisted of two pitot tubes, one mounted ahead of the test section measuring P0 A, and the second in the test section measuring P0 B. The procedure for this experiment is as follows. First, adjust the block setting to 2200, then tighten the side panel bolts, pressurize the external tanks, put on ear protection, then run the first test while recording P0 A and P0 B on the computer. Then we can loosen the side panels and decrease the block setting by 200. This changes the throat area. Repeat the procedure down to a block setting of 800 by decreasing by 200 every time. The Mach number MA for each block setting can be determined from the recorded stagnation pressures P0 A and P0 B.
The stagnation free stream pressure was recorded in gauge pressure, and the pitot pressure was recorded as absolute pressure using LabVIEW. The data was exported to Excel in order to find the 98th percentile. Using the percentile formula, Excel gives a stagnation and pitot pressure for each block size. Those numbers are then used to find the pressure ratio. For the stagnation pressure method of calibrating the supersonic wind tunnel, 14.7 psi was first added to the stagnation free stream pressure. The pitot tube pressure was divided by the stagnation pressure to get a pressure ratio. By using this ratio in Table A2 from the Fundamentals of Aerodynamics book by John Anderson, the shock jump tables, the Mach number for each block size was found. As shown in the table, as the block size decreased, the Mach number increased from 1.97 to 3.3.
The wind tunnel is adjusted and ran using the same procedure as the stagnation pressure lab. Coherent light, meaning the light is of a single hue and minimizes internal interference, is pointed through a slit and at a mirror. The light then passes through the test section to another mirror that focuses the light on a knife edge. The light then continues onto a recording medium. For the NCSU wind tunnel, the medium is a projection on the wall, and the image is captured with a camera. The system allows for visualization of an oblique shock wave on a spear in the wind tunnel. The shock wave angle allows for the determination of the Mach number inside the tunnel. We can do this for varying block positions to calibrate the wind tunnel.
To use the Schillerian method, we would need to determine the angle of the shock beta and the angle of the spike or wedge theta. To find the angle of the shock and wedge, we used AutoCAD on our flow image. In AutoCAD, we measured the angle of the shock lines to the horizontal to find beta, and the edge of the wedge to the horizontal to find theta.
When supersonic flow moves past the spearhead of angle theta, an oblique shock forms with an angle beta. If we assume that the velocity changes only in the direction normal to the shock, we can determine the Mach number in front of the shock with the shown relations.
As you can see in this graph, the stagnation pressure gave an average of 10% lower Mach numbers. Both methods followed similar trends.
To determine which method is more accurate in relating the Mach number to the throat area, we need to look at some possible method errors. Let's first discuss issues with the stagnation pressure method. The first issue is the accuracy of the isentropic assumptions upstream and downstream of the shock wave. For this test, we assume that the upstream and downstream entropy remain constant, while the only losses occurred at the shock wave itself. While this is a good assumption in theory, in reality there are things such as friction which contribute to entropy changes upstream and downstream of the shock wave, not only at the shock wave itself. Another issue is the variation of the pressure data over time. For our wind tunnel, P0 A and P0 B will not remain constant because the flow changes. Therefore, we had to figure out a way to choose what values P0 A and P0 B we would use for our calculations of Mach number. Now let's move on to issues with the Schlieren imaging method. Although these images are direct depictions of nature, there are things that can distort the shockwave images. The first of these is the wedge alignment. If the wedge is not aligned parallel to the wind tunnel flow, images will show skewed shockwave angles from the side. Another issue we have is with projection. If the images are not projected perpendicular to the wall, they will be skewed. The camera and our measurement software may also introduce some types of errors, which will skew the angles and keep us from finding the correct Mach number.
The stagnation pressure method makes more assumptions than the Schlieren imaging method. The stagnation pressure method requires isentropic flow everywhere except the shock, while the Schlieren method only assumes a constant velocity perpendicular to the shock. The problem with the Schlieren method comes with the setup. 1 degree change number by approximately 0.2. These measured angles depend heavily on a precise setup. Errors in mirror placement, light direction, knife edge placement, or camera placement could all affect the measured angles. For these reasons, the stagnation method is preferred.